magnifying glass actually can't see. The picture is supposed to tell you how small it is, so I have to tell you that that is a normal pen point, ballpoint pen point. It could just be one that's 2 feet in diameter. You get the same thing. And the BBC test program card is being displayed on it. So it's micro display. It's actually built onto a silica substrate, micropixel, and it uses CBT type polymer to actually produce the colour light, and works really, really well. It's developed by a spin-out company from Napier University and Edinburgh University, and was going great guns until recently it run out of money. So India's a country that probably has quite a bit of money somewhere. If you've got lots of money, I think it's a great idea. You can have cameras where you look through the viewfinder for what you see as a micro display. You don't need to do the screen. They were working in the sunlight because it's not light not shining on it. You could even have displays in your glasses so you can watch TV without people knowing you're watching TV. Another area of work which Napier is involved in is the concept of using photonic materials for displays rather than electronic. So rather than having an electroluminescent display like we just looked at, where electrons and holes combine together to produce light, we use light to produce light. It sounds too simple to be true, it's certainly too simple. So we use light to generate light. You can also, of course, generate electrical power from light, as we know. So the vision is to produce things like mobile products that require little or no power and can work in bright ambient conditions like direct sunlight. That's the sort of long-term vision. And how does it work? It works basically by having a light guide, polymer, which contains a fluorescent dye, or dyes, and it collects light from the ambient, transfers it through the light guide, and re-emits it somewhere where you want it to, so there's a lot of optical design, but only of one particular colour, one particular wavelength. So you get amplified light. Each dye is almost photon for photon efficient in transferring. Obviously, you lose energy. These are going from blue light to red light. So blue light is the most difficult one to generate. So when you want to make a display, all you do in the colours is use coloured light material dots. And like the little crystal display in front of me, there's a shutter in front of it which turns the light off. In other words, it's on all the time. Unlike electroluminescent devices, you do the opposite way. You put power in to turn the light on. So they're complementary rather than like competitive technologies. What each has its own advantages, which are quite different than the others. And Freelight is a Napier University spin-out company who's been trying to commercialise some of these aspects. The trouble is, it's got perhaps too many applications, and it's difficult to entirely tie people down to which one is the one we're going to put all the money in. But this is an early demonstrator of perhaps the world's first sunlight viewable display. I tried this yesterday and found the video clip didn't actually work, so I won't attempt to do it. But all that happens actually is the numbers change in front of your eyes. What we've got is a light collection colouring device, a Freelight, with a liquid crystal shutter from a £15 toy from Toys R Us to block out most of the light. It's not terribly good at it, it's not very efficient shutter, but it's enough to produce contrast you can see. And it doesn't require any power other than the electrical power to the shutter on the liquid crystal. There's no backlight. So you can have an red, green, blue display, which you can then mix and match to make any colour you like. It could work in a football stadium. It would work wonderfully well in sunrise and sunlight India. It would even work in an overcast day in Glasgow. Because as long as there's light, you get X times the light. The challenge, of course, is blue. Blue is the hardest colour to make, and we've done quite a lot of work on blue dyes. So, to sum up, what can we achieve here? Polymers today can be made with high conductivity, or obviously we can do open, they can be tailor-made, they can be doped to become PN junctions, they can be used to fabricate diodes and transistors and light emitting, so we can actually print printed circuits. It's not like etching away copper and putting down bits of metal, but by actually printing conductive polymers. We're never, at the moment, going to get anywhere near silicon for performance in terms of speed and how small a feature we can make. But for larger areas, that's not a problem. We can also use them to collect light and use it to produce either a display or to enhance photovoltaics. Because photovoltaic cells are very expensive because of silicon. They're not terribly efficient anyway. But if you have a polymer one, it might not be half as efficient, but you can make it roll to roll and roll it out of the roof of your house or line the walls with it and produce electricity for large areas. And of course, photovoltaic devices are particularly sensitive to things like green light. They don't like infrared, it fries them. They don't particularly work very well with shorter wavelength blue light. They usually work very well around the green area. So again, you can use fluorescence in combination in order to achieve that. So again, just to conclude, electrical and optical properties of polymers are good. Of course, the real benefit here is the ease of processing. You compare this to silicon wafer production, where you spend hundreds of millions of pounds building fabrication plants somewhere in Far East usually, then this is something that you can't quite do in the shed. You do need a clean room, but you can do it anyway. You need to spend hundreds of thousands of pounds, maybe £1 million, but not £100 million. And size is not really a problem. You're not limited to the size of a crystal like on silicon. If you can make a plastic sheet or a plastic film that large, then you print the crystal can make it fine. But it does, of course, all rely on the polymer chemistry. So polymers are, I think, very much the solution to the challenge of the future. I know people get hung up about the problem with the plastic bags and things of that nature, but they're very much part of the solution rather than the problem. And we just need to be a little bit more inventive in the way that we think about using them. And, you know, blue skies are possible. Well, green is actually easier. Thank you.